Professor, can I ask you a quick question about the homework?
Sure. What's up? Hello? Can you
So,
hear me? Oh,
for part A, um, so I try to use the equation where we have to solve for m, and then the changes in theta. Is that the correct equation?
yeah. So for that one, yeah, all you have to do is compute m, and then the number that goes in front of the exponential. That's just the difference in temperature between the
Temperature,
base of the
yeah.
fin and the air.
So when I was calculating for m, it didn't give me the same numbers as your solution.
Okay, hang on. Let me see. Let's see. I was changing the numbers around on this one a little bit, so maybe I didn't update my answers.
So can I just tell you what I did for, at least for M, when I was
Yeah.
looking for M, I did 300 times pi times 0.12 divided by 30 times 0.12 squared times pi, and then square rooted that.
Yeah, that should be it. Let me see.
So, I don't know, maybe it was, because I tried it, I'll just try this again.
And let me recalculate. Let me see. Okay. Can you tell me what you plugged in again?
So I went 300 times pi times 0.12 over 30 times 0.12 squared times pi, and then when I square rooted it, I got 9.1, about 9.13.
Okay. So the I think your error is actually up here up top, because the perimeter, you have to do 2 pi times r, not just pi times r.
Oh, okay.
Yeah, so there should be a 2 up here. Yeah, try again with that 2, and then I think you should get it. Were you able
Okay.
to get the right M?
Yeah.
Okay, great.
Why was it 2 pi? Was it something in the directions that I missed?
It's it's just the perimeter of a circle. So perimeter of a circle is pi times the diameter. But then what I gave you
Oh,
in the
the
problem,
diameter.
yeah, what I gave you in the problem was the
The
radius,
radius.
not the diameter.
That makes sense. Okay. All right. Thank you.
Yep.
How was your weekend, Professor?
It was good. Yeah, it's
Yeah.
well, one of my good friends, his cat passed away recently, so we hung out with him just to help him feel better. So just us and a couple friends, but it was nice because we hadn't seen each other in a long time because of the pandemic. But you know, we thought this was a good time to do that. How are you?
Good. A little tired. The usual.
Yeah, yeah, it's getting up towards midterms.
Yeah. Question. Do you know if is there still talks like of going back to school, or are we still doing the online thing for next
So
semester?
So we're it's I'll tell you that there's a push from the state to have the language that they're using is predominantly in-person classes in the fall, but they haven't really given a number. That's the only word that they've used to describe it. So honestly, it's kind of a mess right now because I think the state wants to push for more in-person classes, but there's not really a good plan right now, um, and there's a lot of a lot of people are still kind of feeling uneasy too. So I think it's something that's just going to evolve. Probably it's going to keep going until the summer. I would say all this debate and discussion.
Yeah, because like my other question would be like, are you guys, if you guys were gonna do in person, are you guys gonna have class at reduced capacity, or are you gonna do like half students in class and half at home,
Yeah,
or
yeah, all fair questions. All fair questions that no one has the answer to right now, unfortunately. So it's going to be a challenge. I mean, it's we've had meetings 3 weeks in a row to discuss it, and I feel like we haven't really made any headway on it. So it's yeah, just kind of stay tuned, and when I hear stuff, I'll make sure to pass info on to you guys. Okay, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? How was everyone's weekend?
yeah, homework's due on Wednesday, right?
Homework is due on Monday, I believe. So a week from today, because we still haven't got we haven't gone over. Well, you should only be able to do just the first two problems on the homework, but all of the multi-D and the transient heat conduction we haven't covered yet. So we're going to cover that this week, and then the homework will be due on Monday. Yeah. Mm-hmm. All right. So there's that. The other thing that's going to be happening next week is our midterm. So we're already up on our first midterm exam for this class. Okay. And so, on this first part of the class, I'm going to discuss the midterm. I'm going to tell you what I'm going to, give to you guys in terms of study prep and also the format on the exam. And then from there, we'll pick up where we left off last week. I think we left off right on 2D heat conduction. So I want to do at least, one or two examples with that, and then we'll launch into our next topic, which is unsteady heat conduction. Okay. All right. So besides the exam, are there any questions I can answer from what we covered last week, or anything on the homework? Okay. All right. So let's talk about the exam. All right. So the exam is going to be next Wednesday. So that's Wednesday, March 3rd, I believe. Right. So it's going to be an in-class exam. Well, I mean, as much in class as we can right now. So it's going to be 75 minutes. Okay. Right. So during that 75 minutes, you don't have to be on Zoom or anything like that. But I will be on the Zoom call. If you want to come in and ask questions. I'll be available on Discord as well if you want to ask me questions on there too. So if you want to send me just a direct message on Discord, I can answer on there. But the time limit is going to be 75 minutes. Okay. 75 plus some 15. So I'll give you until 4 p.m. on Wednesday, just so that you have some time to scan and upload your solution, because I know that that takes some time too. Right? Okay. And so the format of the exam is it's going to be similar to the homework. So there's going to be a short answer portion and a problem solving portion. Okay. And so right now what I have planned is 3 short answer questions. Okay. and two problem solving questions. The short answer questions will be worth about, in total, 40% of the points. Okay. And the problem solving questions will be worth 60%. Okay. So this is usually how I do my exam. So I place a lot of emphasis on the conceptual stuff because I think the conceptual stuff is really important. Because in reality, 2 years after you've taken this class, you're probably not going to remember, how to solve the heat equation. But what I do hope that you'll retain is, some intuition for how heat transfer occurs. Because I think that's the thing that will ultimately help you out most in your job. Okay, so that's why I put a big emphasis on the conceptual questions. Okay. In terms of what I'm providing you, so I've already posted a study guide. And so you can find the study guide in the files section of the Canvas site, or if you go to week 5 on our course outline, then you'll see the study guide posted there as well, okay? And so the study guide, all it is basically just a collection of all of our learning objectives that we've been going over, over the past few weeks, but I've split them up. So I've split them up into a conceptual section and also a problem solving section, okay? And that's mostly just to kind of help you guys study. And so if you're gonna, one thing I would recommend when you're studying for the exam is definitely use the study guide and definitely pay attention to the conceptual question because the conceptual learning objectives, I basically write them out as if they were questions. So if you can kind of go through and answer all of those, learning objectives for the conceptual part, you're going to be in great shape for that part. And then for the problem solving, you have all the homeworks there to give you practice. Right? In addition to that, I've also posted some suggested problems too on the study guide. Okay, so at the end of the study guide, you'll see that I've listed out some textbook problems that I think are good for for additional practice. So if you want to do some additional problems besides the homework, you can check out those problems on the study guide. Okay? And if you're doing those additional problems, what I would recommend is you don't have to do the problems all the way to completion because I think that takes a lot of time. And so I would focus just purely on, how do you set up the problem? So, write out what equations you would use and, how would you actually go about solving it? But actually going through the mechanics of solving it, I think, pick your spots. I mean, don't spend too much time on that stuff because, I think you get the most practice in setting it up. Okay. All right. So in addition to this, I plan on also doing a review session. Right, but the review session is going to take place outside of class hours. So what I'm going to do is I'm basically going to record probably on Friday afternoon. I'm going to record a video, probably about the same length as the lectures, about an hour 15 minutes, just helping you review for the midterm. And I'll have that posted before the weekend, so you can use that to study as well. Okay. And so for the review session, because it's only going to be the length of a lecture, I'm not going to have enough time to cover absolutely everything. And so what I'm going to do is after Wednesday's lecture, I'm going to post a poll on Canvas for you to vote on, what topics that you want to see most on the review session. Okay. And so, in the review session, I'll probably cover at least the top 2 and maybe a little bit of the third topic from the poll. Okay. And so the reason I do this is because, I think a review session, for it to be useful, I don't believe just going at, 600 miles an hour and just covering absolutely everything. I really want to go in depth in the topics that people seem to be struggling the most with and make sure that, I give you some more information and more help with that because I think that's going to be more useful. Okay. And so, when I post the poll on Canvas, I'll send an email to announce it. And please vote on the poll just to make sure that your voice is heard. Okay. And a word of advice for the poll. And so this happens every single year, no matter how many times I say it. When you vote on the poll, don't vote on everything because that's basically the same as a no vote. Because when I'm looking at the poll, responses, I'm looking at kind of relative differences in between the different topics. And so if you vote for everything, That's literally the same as nothing, because then all the topics kind of go up the same amount, and I don't see any relative differences. So, before the poll, before you vote in the poll, look at the study guide, see, think about what do you feel the most weak in, and then just vote on those 2 or 3 topics that you want to see the most. Okay, and that's going to be basically the most helpful for me. Right? Okay, so are there any questions on the exam?
I have a quick question.
Yep.
Would you still, I know you're giving out a study guide, but would you still recommend doing some of the problems in the notes, or should we just more so focus on the study guide problems?
No, absolutely. Yeah, definitely go over all the examples we did in the class, go over the homeworks that we've done. All of that is really good practice. So usually my policy, and I know for those of you who had me last semester, I kind of strayed from this a little bit because of the 24-hour exams. But usually my policy for the exams is to write exam problems that are a little bit easier than the homeworks. And so the homework problems, by design, I give you really challenging problems, mostly just because there's much less of a time constraint on your homework. But on the exam, especially something like this, you're only going to have 75 minutes, and so I'm going to give you much simpler problems on the exam, just because there's just hardly any time to do anything. And so if you can do all the homework problems and you can understand them, then I'd say you're in great shape for the exam, because the exam problems are going to be a step down from that.
Okay, thank you.
Mm-hmm. All right. Any other questions on the exam? Okay. All right. So the exam's next week. So definitely don't be afraid to ask questions. So I'm always available by email or by Discord. Just reach out. I'm going to help you out, guys, as much as I can. Okay. All right. And so let's pick up where we left off last week. And so where we left off last week was on 2D conduction. Okay. And so the idea with 2D conduction is, it's basically the same idea as all of our conduction problems so far, except now we're working in multiple dimensions. Okay. And the reality with this is that, and we hardly spend any time on this in the class relative to other stuff, because the reality is, once you start getting into 2D and 3D, things start to get really, really complicated. Okay. But what we can do in 2D is we can analyze specific situations that have a particular geometry. Okay? And so we're going to focus just on those. Right? And so the reason we focus on these is because these are geometries that people have examined or analyzed in terms of heat transfer many, many times in the past. And so we have a lot of data and we have a lot of experiments regarding these things. Right? All right, question. So are the topics discussed this week on the exam? Yes. Yeah, so everything that we cover this week will be on the exam. Yeah. So what we're covering this week is called transient heat conduction. And so that will be on the exam. That's on your homework too. So that's problems 4 and 5 on your homework. Yeah. Okay. And so you might be asking, what specific geometries are we looking at? Or what do I mean in particular by specific geometries? And so the geometries that we're going to consider are summarized in table 4.1 in the book. Okay. And what this table shows you is specific situations that have kind of happened a lot in the history of engineering heat transfer. Okay. And what you'll be able to do from this table is that depending on the certain geometry, you'll be able to compute what's called a shape factor. S. Okay. And the shape factor is a function of just the geometry, right? And so once you have that shape factor, you can use that to compute heat transfer. Okay. And so the formula that we have here is like this. Right? So we have Q is equal to S, where S is the shape factor that we're going to get from the table, okay, times K. K is our thermal conductivity, okay, and then delta T, okay. Right? And so we basically set this up the same as a thermal resistance, right? And so if you kind of think of it like this, right? So we have T1, T2, okay? This resistor right here is basically 1 over, or this resistor here is just, yes, just 1 over SK, okay? Right? And so this product of the shape factor times the thermal conductivity is, you can think of it almost as like a resistor that we have in a circuit, okay? And so basically the way that you do these 2D problems is you look at the geometry. First thing you do is you go to table 4.1 and then use that to compute S. And then once you compute S, then you can basically just form a thermal circuit and then compute the heat transfer based on the temperature differences, okay? All right, any questions on this? This was just kind of a recap from last time before we jump into an example.
Yeah, quick question actually. So on the exam, will we need to have our book ready to look at the tables, or will the tables be provided, or will you just give them out?
Yeah, so for the exam, I would give you the formula for the shape factor. So usually I'm not a big fan because, like, you know, in person, you know, I don't want to print out like a bajillion tables for everyone. So usually for these things, I'll give you the formula for the shape factor that you would use. Yeah. Yeah. Mm-hmm. Okay, so let's do an example. Okay, and so let's say that in this example we have a pipe that's carrying very hot fluid, okay, and it's buried within the earth. Okay. Okay, and so the geometry looks like this. So let's say that we have, here's the ground, okay, and then underneath the ground we have a pipe. And so let's put some numbers on this. So let's say that the earth surrounding the pipe has a thermal conductivity of 0.8 watts per meter K. Okay. And this is the thermal conductivity of basically the dirt that's surrounding the of the pipe. Okay. So out here we have dirt basically. Okay. Let's see. So let's say the diameter of this pipe is going to be 15 centimeters. Okay. And then the length of this pipe going into the page, we'll say is 4 meters. Okay. Right. And then in addition to that, we know that the depth on which the pipe is buried underground, that depth is 20 centimeters.
Did you say the diameter is 15 meters?
15 centimeters, sorry. Yeah, that'd be a huge pipe if it was 15 meters. Okay. Okay. And so let's put some temperatures on this guy. So and so let's say that the pipe is is held at a constant 75 degrees C. Okay, so T pipe. Okay. And then the earth, the temperature of the dirt that's surrounding it, we'll say that this is 5 degrees C. Okay. Okay. All right. And so what's going to happen in this situation is that, you know, because the pipe here is relatively hot, heat is going to leave this pipe and it's going to basically come out through conduction into the dirt. Okay. But, you know, because we have, you know, because the depth here is only 20 centimeters, we have kind of a multi-dimensional heat conduction problem here, okay? Because some of this heat is going to come up and it's going to realize that the ground is kind of, right here. And so it's not quite the same as like a radial heat conduction situation, because, we don't have just purely radial heat conduction. Okay? Some of the heat's going to come up and it's going to come this way like that. Right? And so what we have here is a 2D situation that we need to compute a shape factor for. Okay. And so in this problem, what we want to do is we want to compute the heat loss from the pipe. Okay. All right. And so, because we have this this 2D situation, first thing we have to do is we have to look at our table 4.1 and see if we have any geometries that look similar to this. Okay. Okay. And so in this particular case, this geometry is kind of the same as a horizontal isothermal cylinder buried in a semi-infinite medium. Okay. And so if you look at the notes, page 15 of note 03, you'll see that this is kind of the second entry in the table. Okay. So I'm not going to write out the whole name of this, but in other words, this situation here is in the table. Okay. Right. And so from the table, you'll be able to compute the shape factor. Okay. Okay. And then from the notes, you'll see that the formula for the shape factor is 2 pi L divided by hyperbolic cosine inverse of 2z divided by d. Okay. And so all we have to do here is basically just plug in for all the numbers here. Okay. And so we have everything from the problem. And so we know from the problem that L, which is the length of the cylinder, L is 4 meters, right? Z here is the depth that it's buried. And so actually, if you look at table 4.1, you'll be able to see that Z is that length. Okay. And so Z in this case is 0.2 meters. Okay. And then D, which is the diameter of the pipe, we know is 0.15 meters. Okay. And so we plug all these guys in and we get a shape factor of 15.35 meters. Okay. Okay. Now that we have that shape factor, we can use it to compute the thermal, basically the 2D thermal resistance for this pipe. Okay. All right. Any questions on this? Okay. All right. So let's set up.
Professor, I had a question real quick.
Wait.
Sorry.
Yeah. What's up?
When computing the hyperbolic sine or cosine, can we just use something online? Because I don't know if I can compute it with my calculator.
Oh yeah. If it's if you don't have the button on your calculator, then you can just use an online calculator. Yeah.
Okay. Thank you.
Yeah. Okay. And so let's set up our thermal circuit. So in this case, we just have one resistance. Okay, and that's the 2D resistance, right? In the homework, I give you a problem where you have more than one resistance, but for here we just have one. Okay. Right. And so on one side we have the T pipe, okay? And on the other side we have the temperature of the dirt. Okay. Right. And so we know the 2D resistance here is going to be 1 over S times K. Okay. And so Q here is going to be T pipe minus T dirt. Okay. And so simply just the temperature differences between the nodes in our circuit divided by R2D. Okay. And so if we plug in everything from the problem, what we get is 859.6 watts. Okay. Right. And so these 2D problems, you know, as long as we're limited to the geometries that are in table 4.1, you know, these problems are pretty straightforward. So we can just, it's basically just, you know, find the formula for the shape factor, plug in for it, and then use it in this expression here. Okay. All right. Any questions on this example? Okay. So there is one more example in the notes on 2D heat conductions, and so that's a good one too. So that's basically shows you how to combine different shape factors. But I do want to, but I think, you know, instead of that, I think I'm going to give you guys a hint on the homework. Okay, and so I think it's problem 3 on the homework. Problem 3 on the homework asks you to find the total amount of heat transfer in a square pipe. Okay. So it looks something like this. Okay. And what I tell you in the problem is that there's a fluid flowing on the inside. Okay. Right. Actually, let me use a different color for that. Right. Right. And so since this fluid is flowing, then we have two things. So we have its convection coefficient, and we also have its temperature. Okay, so we'll call that T infinity I. Okay. And this pipe here goes like this. Okay. And then on the outside of the pipe, we have another fluid. Okay. And so on the outside, we have fluid 2. And so this also has its own H and also T infinity. Okay. Right. And I think in the problem I asked you along the lines of solving for the heat transfer and maybe a surface temperature. Okay. Okay. And so the way you're going to solve this problem is, you know, since it's kind of a square block like this, you can't just use radial heat transfer, right? But what you can use is you can use 2D heat conduction, right? And so for the block, or for the square pipe, I would say, the square pipe, you can find its resistance using its shape factor, okay? Right. And so if you look in table 4.1, you'll see that, you know, a hollow square like that pipe has a shape factor too. Okay. And so I gave you all the numbers that you need in the problem, so you can compute that shape factor. Okay. The difference between this one and the previous example that we did is that the two fluids will also have their thermal resistances, right? And so for those, you just plug in the convection resistances, right? Right, and so we're going to have convection of our convection of the internal fluid, and also our convection of the external fluid. Okay. And then on the two ends right here, we have the temperatures of the fluid itself. So T infinity I, and then also T infinity O. Okay. Right. And so in this problem, you know, you have 2D heat conduction, but you also have convection heat transfer as well. Okay, so you need to take that into account into your circuit. So make sure that you have 3 resistances in your circuit for that homework problem. Okay. All right. Any questions on this?
That T infinity I, is that also the surface temperature of the inside walls?
No, it's not. So that's a good observation. So that's the temperature of the fluid itself, and so that's going to be different from this temperature right here. And so this surface temperature would be kind of the temperature at this node right here. Yeah. And so, you know, because we have convection, then those things are different. Mm-hmm. All right. Any other questions on this? Okay. All right, so let's go ahead and jump to the next set of lecture notes now, which is on transient heat conduction. And so transient heat conduction, what I mean by transient is that, these heat transfer situations are going to vary with time. Okay. Right. So kind of in a nutshell, these are situations where the temperature of an object is changing with time. Because up to this point, we've kind of been neglecting time, right? Because if you kind of remember from all of our heat transfer or heat equation examples, we've assumed what's called steady state, right? And with steady state, then we neglect that derivative with respect to time. Okay, and so now we're going to lift that assumption. Okay, we're going to lift that assumption, but also put a bunch of other assumptions on it just so we can solve the problem. Because in reality, if you're solving the full heat equation, that's a PDE, and that's a little bit too much to do in this class. Okay, and so we're going to be basically solving problems with a different set of assumptions. But what this will do is this will kind of open up your playbook for what kinds of situations you can solve heat transfer for. Okay, because in reality, there's a lot of heat transfer is time dependent processes, right? Because so if you think just like you're baking something in an oven, right? Or you're heating something up, right? Anytime where you expect the temperature of something to go up with time or to go down with time, these are transient situations that you're going to need to apply a different set of theory than what we've done before. Okay. And so to kind of express that mathematically, basically what we're saying is, we're looking at situations where the boundary conditions, whether this be temperature or heat fluxes, suddenly change. Okay. And so personally, I actually really like this unit because there's a lot of examples that you can cook up for transient heat conduction that can happen in the kitchen, right? And so a lot of cooking is, controlling the amount of heat that goes into your food, right? And so whether you're just, you're simply microwaving a hot pocket or, or you're making a roast chicken, those are cases where you expect your food temperature to go up with time. And as such, we can apply this theory to those kinds, okay? And so our goal in this situation is to basically solve for temperatures, okay, which is going to be a function, but now our temperature is going to be a function of time, not with space. And you'll see that the end goal for a lot of our problems is going to be t as a function of little t. Okay. And so we're going to talk about, how do we go about solving this? What factors, affect this time of evolution, right? Because now it's going to be a lot more than just thermal conductivity. So now we're going to talk about, the density, the thermal capacity of these objects. Okay, so all that's going to play a role, right? And so in the end, you'll be able to solve for this function here. Right? And we're going to use a very special method to do this. Okay, because just kind of like what I just mentioned, in reality, solving general time-dependent heat temperature distributions is something that's really difficult since it's a partial differential equation. But if we make a lot of assumptions, we come across this method, which is called the lumped capacitance method. And the reason it's called lumped is because basically our big assumption here is that the temperature in our object does not vary with space, okay? Or in other words, our object, whatever object we're considering, is the same temperature all throughout. Okay. And so it's basically going to have the same temperature on the surface as it is at the core and at every point in between. Okay. And so if you've ever, baked a pizza roll, you know that this is not true, right? So you bake a pizza roll, you might seem like you can touch it, but as soon as you bite into it, your mouth is just destroyed because, you just put hot lava into your mouth, right? And so that would be a case where it's we couldn't apply the lump capacitance method because the outside seems cool, but the interior is really hot, okay? But just for the sake of simplification, we're going to assume that everything is kind of the same temperature, right? And we'll talk about how you can actually judge or how you can actually compute whether how valid this assumption is going to be. Okay. Okay. So any questions on any of this? Okay. And so let's do kind of a derivation / example at the same time, okay? And so in this kind of example, just to kind of motivate our equations, let's say that we're taking a hot piece of metal, okay? And then we're dunking it into a water bath. Okay. All right, so the situation kind of looks like this. Okay, so we have a large tub of water here. Okay. So there's our water. Okay. And then let's say that we have a really hot piece of metal, and then we're just going to throw it into the water. Okay. Right. And so our metal here, piece of metal, the shape doesn't really matter. So I'm going to draw it with the shape of a potato. Okay. And so at the initial time, so basically right when we throw the piece of metal in there, it has its own initial temperature. Okay. Okay. And so we'll call that initial temperature Ti. Okay. Meanwhile, the water here has its own temperature. Okay, so we'll call that T infinity. And then we'll say, because the water is cooler, we'll say that T infinity is less than Ti. Okay. Right. Right. And so before we jump into the mathematics, let's just talk kind of intuitively what we expect to happen, right? And so when you put a hot piece of metal into a hot water bath, generally what you'll expect is that the hot metal will rapidly cool, right? So its temperature will drop. And it'll keep dropping until it reaches the same temperature as the water. Okay. So that's generally kind of what you expect to happen when you put something hot into something cold, right? Especially when we assume that this water bath is fairly large, and so we're going to assume that the temperature of the water doesn't change that much, but the metal temperature is going to change fairly rapidly. Okay, and so generally what we expect is the mathematics should kind of support this conclusion here. Okay, all right. Any questions on this situation so far? Okay. All right, so let's start talking about, how do we actually, represent this mathematically? Right? And so what I'm going to do is I'm going to take the piece of metal out, and I'm going to perform an energy balance. Okay. So here's our piece of metal. Okay. It changed shapes between the upper picture and the lower one because I'm terrible at drawing, but just use your imagination to say it's the same. Okay. And let me draw just a control volume around this guy. Okay. And so generally what we expect, when we put this hot piece of metal in there is that heat is going to escape, right? Right, so we're going to have a heat transfer that comes out, okay? And the primary mechanism through which, the heat's going to come out is going to be through convection, okay? Okay. And so because, as the metal sinks to the bottom, there's going to be water that's kind of flowing on the outside of the metal, okay? And so the primary way through which heat leaves the metal is going to be from convection, okay? Okay. And so the other thing that we have to keep in mind here is the internal energy of the metal. Okay. Internal energy, if you remember from thermodynamics, this is just another name for its temperature, basically, right? And so the lower its temperature gets, a lower amount of internal energy is there. Okay. Because all the heat that escapes through convection, all of that heat has to come from somewhere, right? So we can't just create energy out of nothing. And so what we're basically going to say is that there's going to be a balance in between the amount of internal energy inside the metal and the amount of heat that gets lost due to convection. Okay. And so the balance here is basically that we have E internal plus Q out is equal to 0. Okay. And so, the amount of, basically the way to say this in words is that the internal energy of the object is going to be decreasing, and the rate at which it's decreasing is exactly the same as the amount of heat that's leaving due to convection. Okay. All right. Any questions on any of this?
So do we just make an assumption that for the boundary that anything that goes past it from the inside to outside is a negative then?
Yes. Yeah. Yeah. So we're going to put a negative on this Q out. Actually, so let me put the negative right here. Yeah. So we can move. What we're going to do is we're going to put 1 on the other side of the equation and say that they're equal. And I'll put a negative sign there so that they're equal. Yeah. Okay.
Thank you.
Mm-hmm. Okay, so let's write expressions for each of these two guys. So we'll write an expression for Q convection, and we'll write an expression for internal energy. Okay. Okay, so let's start with convection because we've seen that kind of a dozen times at this point. Okay. Okay, and so for Q convection, we're going to replace that with our familiar Newton's law of cooling. And so Newton's law of cooling says that Q convection is equal to H times A times T, T of the metal object minus T infinity, okay? Okay. And so for the internal energy, we can basically use this formula right here, okay? Because the internal energy, it's going to be a function of, the temperature, of course, but it's also going to be a function of its density, its volume, and also its specific heat capacity. Okay. So we have E dot internal is equal to rho times V times C times dt dt. Okay. Right, so let me go ahead and label everything here. And so this rho right here is density. Okay. This V here is volume. Okay, so simply just the geometric volume of the object. And this C right here is specific heat. Okay. And so the units for all of these guys are given by the following. So for density, we have a mass over volume. Okay. And so usually for density, you might have something like kilograms per meters cubed. Okay. For volume, you just have volume. Okay, so that's just meters cubed. And then for specific heat capacity, we have the units are this. We have energy. So energy could be something like joules. Okay. Divided by mass times temperature. Okay. All right. And so we put all that together, then we end up with the following. Okay. Well, actually, Nicholas, I misspoke. So actually, there shouldn't be a negative here because we actually need a negative in our solution. Yeah.
Oh, okay.
Yeah. Okay. And so when we put it all together, we have you know, we're basically adding these two guys together. So we have rho. The negative comes out kind of naturally from everything else. Yeah. So we have rho VC dt dt plus HA times T minus T infinity equal to 0. Okay. Okay, and so let's go ahead and move this HA, T minus T infinity, over to the other side, right? So we have rho VC dt dt is equal to minus HA T minus T infinity, okay? All right, so here let's make a substitution. And so since we have this T minus T infinity, just like we did with our fin equations, let's do things in terms of theta, which is our excess temperature. Okay, and so we have theta is equal to T minus T infinity. Okay, and so that helps us simplify this quite a bit. So in the end, we have rho VC times d theta dt is equal to minus HA theta. Okay. Okay. So this right here is really nice because what we have is a first order ODE, right? So we just have one derivative with respect to time. And a nice thing about this is that it's separable. Right. So we'll be able to actually solve for a very simple solution here, you know, just based on separation of variables. Okay. Okay. Any questions on this before we go about solving it? Okay. Okay. And so let's go ahead and separate the variables. Okay. And the way we're going to do that is we're going to put everything with theta on one side of the equation and everything that doesn't have theta on the other side. Okay. And so if we kind of manipulate the math of this problem, we end up with the following. Okay, so on one side, we have d theta over theta. Okay. And this is equal to minus HA all over rho VC dt. Okay. And yes, I know that it's mathematical sacrilege to kind of break up a derivative like that, and I know that's not what a derivative is, but you know, it works well for this, and we're engineers, so you know it's okay. Okay, because from here, what you can do is you can just simply integrate.
I missed where d theta came from, because wasn't there a d capital T dt?
Yeah. So we replace the d capital T dt with theta, because we define theta as t minus t infinity, and then we take when we take the derivative with respect to t, t infinity is just a constant. So when we take the derivative of that, it just goes away. So we have d theta dt is equal to dt dt.
I see. Thanks.
And so when we integrate this, on the left-hand side, we just have, you know, the integral of 1 over theta d theta. And so that's just going to be the natural logarithm of theta. Okay. And then on the right-hand side, we have, you know, everything in this coefficient here, HA over rho VC, all these guys are constants. We have the integral of a constant dt. And so we have minus HA all over rho VCT. Okay. Plus C, right? Where C here is our arbitrary constant. Okay. Okay. And so that guy just comes out just from the integral. And so what we can do from here, just to get a you know, a function of theta, is we can exponentiate both sides. Okay. So we're going to you know, e raised to both sides. And what that's going to do on the left is it's going to cancel those guys out. And so we have theta of t. Okay. And on the right-hand side, what we get is e to the minus HA over rho VCT plus C. Okay. And then just as customary for these kinds of problems, we have, you know, e times e to the h minus HA over rho VCT. Okay. And since we're adding exponents here, that's the same as, you know, multiplying it, right? And so since we have e, which is a constant, raised to c, which is another constant, we usually just bring that guy out in front just for simplicity's sake, okay? And so what we get in the end is theta of t is equal to a, which is another constant, times e to the minus HA over rho VCT. Okay. All right.
Maybe we could use lowercase a so we don't have two capital A's.
That is a good point. Thank you for that. Yes, that is that would be good to not be confused with our constants here. Thank you. Mm-hmm. Okay, and so what we can do now is we can solve for this lowercase a here from our initial conditions. And initially, what we knew is we knew the initial temperature of the piece of metal, right? And so what we can say is that theta of 0 is equal to theta I, where theta I here is the initial temperature difference between the metal and the water. And so because, you know, we have just a, you know, an exponential here, when we plug in 0, you know, we're going to get this this exactly. So actually plugging in the initial condition here is fairly simple, but I'll do that on the next page. Okay. Are there any questions on this so far?
Can you actually scroll down a little bit? I can't see what you wrote.
Oh, yeah. Let me clear this up a little bit. Hmm? Right. Okay. And so when we apply that initial condition, we have theta of 0 is equal to, I'm just gonna plug in 0 into our general solution here. So we have lowercase a raised to the minus HA over rho VC times 0, okay? And so here we're gonna have a to the 0, and so we just have little a. And then little a here is gonna be our initial temperature difference, okay? And so our final solution is going to be theta of t is equal to theta I times e to the minus HA over rho VC t. Okay. So compared to some of our other solutions, this is relatively simple in nature. Okay. Okay. And mathematically, what we have here is just a decaying exponential, right? And so what we can do here is we can plot the our theta as a function of time. Okay. And so our plot's going to look like this. So initially, we're going to start with a temperature difference of theta I, and then eventually this is going to decay down to almost 0, right? Okay. Okay. And so as time passes, the temperature difference between the piece of metal and the water almost basically goes down to 0, right? And if you remember what we talked about when we first started this this example here, we generally expected that temperature difference to go down to almost 0. Okay, and so in this is a case where the mathematics supports what we physically kind of expect from the problem. All right. Any questions on any of this? Okay. And so even though we have a relatively simple solution here, there's a lot that we can kind of unpack. Okay. And in particular, what I want to look at is this this coefficient here in front of the t. Okay. Because basically all the physical parameters of the problem, which is are the convection coefficient, the area, the density, and all this kind of packed in the same place. So let's look at each of these guys individually and talk about how they affect the time evolution of temperature. And so mathematically, or the term that's usually given to these things is the time constant. Okay. And so let me write it again right here. So we have h times a divided by rho VC. Okay. And let's look at kind of the the numerator and the denominator. Okay. So let's look at the numerator first. Okay. And so we have h times a here, right? And so just to kind of remind you that a here is surface area of the object, right? As is traditional with the Newton's law of cooling, okay? And so in particular, let me write it like this, right? Because this h times a, we've seen this before, because this is nothing more than just our convection, thermal resistance. Okay. And in particular, this is 1 over the convection thermal resistance, right? Because our convection that we've seen before is 1 over HA, okay? And so another way that we can write this time constant here is 1 over R convection times rho VC, okay? Okay. All right, so what does this tell us, right? And so because we have R convection in the denominator here, what this basically tells us is that the smaller the convection resistance, the more rapid the temperature decline, right? Okay. And so basically the less resistance that convection gives you, the faster the temperature is going to go down, okay? And conceptually this makes sense, right? And so, when you have lower resistance, what tends to happen then is that more heat transfer is going to occur, right? And so it's just like a circuit, right? So the less resistance that you have, the more things are easier to flow. And so when heat's more, when heat can flow easier in your object like this, then your object's going to lose heat a lot faster, right? And so if the object can lose heat faster, then this temperature is also going to decline, right? And so there's kind of this inverse relationship in terms of the convection resistance and the temperature, okay? And so putting in terms of resistance, I think, it can be a little bit confusing because you're doing kind of 2 inversions. So let me kind of state it like this, right? And so since we have H and A in the numerator here, okay, basically what this tells us is that if we raise H, okay, or we raise A, okay, or in other words, we increase the surface area of our object, what this will do is that this will increase the amount of convection heat transfer. Okay. And if we increase the amount of Q convection, this will make the temperature of our object decline faster. Okay. Or in other words, it'll cool faster. And so if you, if you increase either of those guys, which are in the numerator of our time constant, that makes it so that, we reach kind of equilibrium a lot faster. All right, any questions on this? Okay. All right, so now let's look at the quantity in the denominator here, okay? So all of these guys actually go together. And all of these, you can kind of think of it as not a thermal resistance, but a thermal capacitance. Okay. And if you remember from circuits, a capacitor is a circuit element that can temporarily store charge. Okay. And so kind of in the same way here, all of these parameters here, they affect how much internal energy the object can store. And so, the more energy that an object can store, the longer it's going to take for, for the object to kind of lose all of that energy. Okay, so that's why all these guys are in the denominator. And so if you increase the thermal capacitance, it'll make the temperature distribution or the temperature time evolution go slower. Okay, and so let's go through each one of these individually. Right. And so the first term here in our thermal capacitance is the density. Right? And so basically, the more dense an object is, the more energy it can store. Okay. And so if you have kind of two objects, one is made of, something that's really dense versus some that's not. The one that's really dense can store a lot more energy. Okay. And so, chemically, the way that you kind of explain this is that, remember, density is kind of a measure of how, densely packed the atoms of that material is, right? And so basically, a more dense object will have more atoms and more molecules packed into a smaller area than something that's not as dense. And so, and the more molecules that you have, the more energy, or the more molecules that are there to basically store energy. Next, let's talk about the volume, right? And so if you increase the volume, this increases the amount of energy that it can store. Okay. And so this kind of makes intuitive sense. If you have kind of a bigger object, naturally it's going to store a lot more energy than a smaller one. Okay. Right. And so the last one we have here is the heat capacity. Okay. And so just like the other two properties here, if you increase the heat capacity, it can store more energy. Okay. And so heat capacity, it's just another physical property of the material that basically tells you, how much energy it can store. So it's separate from the density and the volume. And so heat capacity is, so what this basically tells you that among materials with very similar densities from each other, some materials can just naturally store energy a lot better than other ones. And the heat capacity is something that reflects that. Okay. Okay. And so just to kind of illustrate this for you, let me show you how it affects the curve. Okay. Right. And so here's kind of our base curve, right? So this is kind of the solution that we found from the base case, right? If we let's talk about the resistance first. So if we increase the resistance, or we decrease the resistance, the temperature is going to decline more rapidly, right? And so visually it looks something like this. So basically you have a kind of a bigger drop off. But then the opposite is true for the thermal capacitance. Okay. And so if we increase any of the parameters that we've we talked about there, then you're going to have kind of a shift up in this curve. Okay. And so if you play with any of these physical properties here, then what you should see is that the curve kind of either shifts up or shifts down. Okay. And so that's going to affect, It's not going to affect the starting point because the starting point is always going to be the same. So our starting point is always theta I, but it's going to affect, how rapidly or not it declines. Okay. Right. And so in this figure here, I've just talked about increasing capacitance and decreasing resistance, but you can do it the other way too. And so if you increase the convection resistance, you actually go the other way on the curve, right? And so if you increase the resistance, you're going to go toward the purple side. Whereas if you decrease the thermal capacitance, then you're going to go the other way, where you have a more rapid decline. Okay. All right. Any questions on any of this? Okay. All right. So let's start one more example that we'll probably finish up on Wednesday. Okay. And let's look at kind of the opposite situation from which we just looked at. Okay. Because what we just looked at was we dropped basically something hot into something cool, but what if we drop something cool into something warm? Okay. And so in this example, let's say that we take an ice cube and we throw it into a large bucket of water. Okay. All right, so just like before, we're going to have a big piece of water here, or a big tub of water. And then we're going to have an ice cube. Okay. And so just like before, we're going to say that this ice cube has a initial temperature Ti. Okay. But this time we're going to say that Ti is less than T infinity. Okay. And so the water is basically warmer than our object. Okay. And so what's going to happen is that instead of convection heat transfer leaving the object, we're going to have convection heat transfer coming into our ice cube. Okay. Because the temperature difference is opposite here. Right. Right. And so for this problem, we're going to do the following. Okay. All right. So the first thing we're going to do is we want to solve for the time evolution of temperature. Yeah, we're gonna assume the ice cube is gonna drop. Yeah. Assume ice cube drops. All right. All right. So we're gonna solve for theta of t and plot it. Okay. Let's start with that, and then we'll get to the other parts of the problem kind of after that. Okay. All right, so we're going to assume that we know everything about the ice cube. Okay, so we're going to assume that we know H, A. We know the density of the ice cube. We know the volume. We know C. Okay. Right. And obviously we know the initial temperature difference. Okay. All right. And so actually, if we know all of those properties here, our solution is actually going to look exactly the same. Okay. And so our theta of t is still going to be theta I times e to the minus HA divided by rho VC t. Okay. Because geometrically, this problem is exactly the same. The only thing that's different here is the initial condition. Okay. And so if we take the difference between Ti and T infinity, we're going to get a negative number here. Okay. And so our graph here is going to come from the opposite direction. So instead of an exponential that comes from the top, we have an exponential that comes from the bottom. Okay. And so graphically it looks something like this. And so just like before, we're going to start in theta I. and then we're going to decay towards 0, just like that. Okay. And so this is theta of t is equal to theta I e to the minus ha over rho vct, where theta I is less than 0. Okay. All right. And so it's it's basically the same solution here, but it's just the graph is kind of flipped just because our ice cube is colder than our fluid. Okay. But mathematically, it looks exactly the same because we have the kind of the exact same physics going on. All right. Any questions on this before we wrap up for today? Okay. All right, so that's all we got time for today. So thank you guys for tuning in. And so on Wednesday, we'll finish up these lecture notes on transient heat conduction, and then from there you should be able to finish the homework. Okay. So thank you guys for tuning in today. Have a good afternoon, and I'll see you guys on Wednesday.
Thank you, Professor.
Thanks,
You
guys.
too.
Thanks, guys.
Thank you, Professor.
Thanks.